slides?
Yes, I can see.
Okay. Thank you. Welcome back to the course, the Gyan workshop on AI for data representation, analytics, and visualization. Yesterday, we talked a bit about data and how to represent and visualize data. Quickly go through a small summary. And once again, for those who were late yesterday or didn't manage to attend, here are my contacts. Some of you already contacted me, so feel free to reach out to me anytime. Of course, would be better if we have a discussion here for the benefit of everybody else. But if you have questions later, or if you feel too shy to ask, you can also ask me later. So this was the course overview. Yesterday we covered data science. Today we're going to talk a bit about AI. And this is the reference book and the slides. Some of you also messaged me asking for the slides are here, scientic.net/2025 So as stated on this slide, these are for your own learning purpose. So please do not post them on social media or on your blog. So the important bit of yesterday class was the awareness that even a tool that like ChatGPT seems very intelligent to most of us actually is working mostly on numbers. It's working on words in any language through word embeddings. So basically, it has a very smart way of representing words or characters if we are talking about like Sanskrit or Chinese or any other language. And then once it has done its own computation in the numerical domain, go back to the text domain. So in general, when we talk about representing data, these are the three main methods. So yesterday we talked about one-hot encoding, TF-IDF, also known as bag of words, and finally word embeddings. We didn't talk much about word embeddings yesterday, but we're gonna talk about it in lecture 3. Not sure if today we're gonna cover that. But another very important part of yesterday was how to build a vector space model. So word embeddings are these big vector spaces of 300 or more dimensions. How are they built? And in this image, you can see how I can simply build, in this case, 7-dimensional vector space, where in the rows I have the words that make up my documents, and in the columns I have my documents. So these will be the vectors that are represented in a vector space, how as data points or arrows that go from the origin of the space to the specific data point. Why do we work with arrows? As we mentioned yesterday, it's better to calculate the angle between these vectors rather than calculating a Euclidean distance between points in the space, because that's not indicative of how similar or dissimilar these documents are. So the formula for calculating the cosine similarity looks a bit difficult, but actually it's very easy. If you normalize the space, we can discuss that later if you are interested in knowing what this means exactly, or you can look up this on your own. Actually, it's very simple. It's just a scalar product for every dimension of your space. So for example, if you're in 3D, this V would be just 3. You just do the multiplication of the two dimension and then sum them up all together. We also talk a bit about dimensionality reduction, because as you build your vector space and you keep adding more documents here, for simplicity, we only had 7 dimensions, but in reality, you can expect to have thousands of dimensions. And it doesn't make much sense to work in a 1,000-dimension vector space. So that's why we can use a dimensionality reduction technique like TSVD or SVD, singular value decomposition. It's called T truncated because, as we said yesterday, we cut away the bottom right singular values that are the least representative ones. And so this works a bit like you do when you do JPEG resizing. But mostly vector space looks like this. So when people talk about word embeddings, what are they talking about? They're talking about the coordinates of each of those data points that once again can be anything from documents, videos, images, and whatnot in a multidimensional vector space. This once again is the snapshot of affective space, our own embeddings for affective computing. It's 100, the dimensionality is 100, so each embedding, word embedding, has 100 numbers, which are again the coordinates to find this point in the vector space. And last thing we touched yesterday was what to do with this vector space. So we saw how we can calculate, for example, the similarity between two documents or two data points using either Euclidean distance or cosine similarity. We can also use them for classification with different classification techniques. So we mentioned the important concept of centroid that we use to classify documents, and there are different paradigms in supervised classification. So all these examples, including naive Bayes and KNN that we talked about yesterday, are called supervised because that's when I have some clear classes and labels, so that, for example, I can calculate the conditional probability. And even with KNN, I need to know what are the values of these neighbors to be able to classify new points. We also talk importantly about the trade-off that we need between bias and variance, and that's why neural networks generally are better than more standard classification techniques like naive Bayes or KNN. We also talk about SVM, which has been the state of the art in computer science and classification for more than 10 years and still is heavily used today for simpler problems. Like, for example, when you don't have a lot of training data points, you can use SVM. Also, you can actually use SVM every time you have a linearly separable data, like in this case. So in other words, if you can separate your two classes with a line very clearly, clear cut like this, it's better to use SVM rather than a deep neural network. So this is something that I didn't go too much into details, but you can look up on your own. I'm sure many of you already know SVM, but if you don't, here are some links. Haven't checked if these links work actually, but there are many libraries in Python and MATLAB and many others that that you can use easily for SVM. Last thing we talked about yesterday was clustering. So in all the previous algorithms, I have classes and labels. What do I do if I don't have labels? I can just, in a sense, classify the data based on some patterns. So clustering is about that. I don't have any labels about these data points, but I can already see that there are 3 clusters. So algorithms like k-means helps me to cluster different groups of data that are similar just by similarity, using again the concept of centroid. And then later I can decide what these data points represent. So later on, I can assign a label or a class based on, for example, the medoid, the one that in the middle that is a more representative of the class. And all these examples that we saw, once again, were in 2D, but actually we're still talking about multidimensional vector spaces where I can have hundreds of dimensions. So that's about it for what we talked about yesterday. I'm sure you also have the recordings in case you want to watch those again. But if you have questions, you can still ask me today about yesterday's lecture. And today we're going to talk about, oh, there is Vivek has a question. Yes, please.
Eric, a very good morning to you. I just wanted to ask you a question from the last slide which you had. You have written that clustering generally follow unsupervised learning. So is it a usual thing, or it is like whenever we are doing clustering, it will always be unsupervised?
No, thanks for the question. And there are some classification techniques like self-supervised that are also considered unsupervised. And then with pre-training, like today, a lot of the models are pre-trained. It's not clear cut like in the past. In the past was really just like this. If you have labels, you're doing classification. If you don't, you're doing clustering. But today, actually, it's kind of a gray area because there are a lot of like zero shot learning or self-supervised learning that um, for which I cannot say what you just mentioned. I cannot say that every time I'm doing unsupervised, I'm doing clustering. And also, again, with pre-trained models, some people say that they are unsupervised because you're just using them straight away without training on your own data, but they have been trained, they have pre-trained before on other data. So the definition of supervised and unsupervised today actually is a bit tricky. So thanks for your question because this needs to be clarified.
Thank you.
Okay, so let's continue. Today's lecture is about some basics of AI. So we're gonna touch a bit on neural networks. Once again, I apologize for those of you who already know what a neural network is and how it works. But importantly is that today AI is very pervasive. It's important to embrace the fact that we need to know a bit about AI. And even if we don't know the technicalities, it's important to at least know how to use AI, as it was mentioned yesterday in one of the introductory speeches. So it's also important for us computer scientists to look at all the nuances of AI in other disciplines and also listen to the general public. So if you become an AI expert, you should also be able to answer questions like if someone comes up to you and asks you whether they're going to lose their job to AI. So these are all hot questions that people have been asking for a while, especially those that don't really know the potential and the actual power of AI. So it's important to also read up on a bit of these. So different people have different opinions. I personally think that, like I'm generally very optimistic about AI in a sense that these things have happened multiple times in the history of humanity. We had all these things already happened with the agricultural revolution, with the industrial revolution, the internet revolution. So some jobs will be lost, yes, but new jobs will come up. And so if you're interested in these topics, I don't want to talk too much about this, but there are some interesting reports like the IMF report from last year that talks about AI preparedness. So they even came up with the definition of AI preparedness index, which basically tells you that some of the more advanced economies are the ones that supposedly are more prepared to the AI, the changes that AI is bringing about. But one interesting thing about this revolution this time that is intrinsically different from past revolutions is that for the first time, it's the white collar jobs that are affected and not the blue collar jobs like it happened, for example, in the agricultural and industrial revolution. But there are other things that are worth discussing because now for us adults or young adults, it's very good to have something like ChatGPT that can help us automatize many of our tasks at work and even outside work. But then is it good to give these tools to children? Can ChatGPT hamper the capabilities, like the writing and even speaking skills of those who are just learning how to write and speak? So this is a question that I would like to ask, and not many are talking about. So there should probably be an age at which ChatGPT is allowable. And then there's also the big question of whether we should allow students, even at the university, to use ChatGPT to write reports and whatnot. There are also very interesting discussions to have on where are we going with large language models. We just wrote this short, you could say funny article on the plagiarism singularity conjecture. So I don't know if you guys heard about the infinite monkeys conjecture. So there are people who actually wrote articles on this, like how long will it take a monkey to randomly type a specific word or a phrase like to be or not to be? Because at random, if you have infinite monkeys and infinite time, then there is a probability, although very small, that a monkey could write even a novel of Shakespeare. At least that's what the infinite monkeys conjecture is about. So in this paper, we say, okay, if we replace the monkeys with the large language models, then we're going to reach a singularity pretty soon where basically everything will have been written already. And any scientific paper, any novel, any poetry will be plagiarized. So this is a bit extreme, but it's also important to reason on where are we going with large language models, what are we using them for, what a large language model can do. And this is something that we'll discuss again in lecture 3. The next thing I want to do is a bit of clarification on the terminology, because today when you read the news, you see that these 3 terms are used pretty much as synonyms. People talk about AI as equivalent of machine learning and deep learning. In reality, these are all subset of each other. So deep learning is a subset of machine learning where we are using specific types of neural networks, the deep neural network like convolutional neural network, recurrent neural network, transformers that we'll see together in the next few slides. But then there is also the rest of the algorithms, and some we have also seen them in the past lecture, like SVM is machine learning. You could say naive Bayes and KNN are also machine learning algorithms. But these are the ones that are not deep networks. So when you talk about machine learning, yes, you could be talking about deep neural networks too, but in general, you're talking about a much bigger umbrella that also covers all these other machine learning algorithms that are not deep neural networks. And last but not least, AI is also very much used as a synonym of deep learning today. But actually, AI contains deep learning, machine learning, and also the so-called symbolic AI, knowledge graph, semantic networks, even ontologies are what it's called symbolic AI, while machine learning is more sub-symbolic. Why? Because instead of using symbols like letters or characters, we are using numbers, as we said yesterday. So let's reason also on the term artificial intelligence. The first term that I want to reason about is intelligence. So every one of you surely knows what intelligence is, but if I ask you to define intelligence in a way that you could build intelligence from scratch, that's not a very easy task. So Richard Feynman said if to truly know the meaning of something, you have to be able to build it from scratch. And we don't actually know how to build intelligence. Yes, deep neural networks are a very good way of replicating intelligence, but then claiming that they are true intelligence, it's a bit too much, maybe. And another thing that we usually do when we talk about intelligence is that we assume that we are talking about IQ, but there are so many other different kinds of intelligence, like EQ or even CQ, cultural intelligence, physical intelligence, and so on. So yeah, you can find many different definitions of intelligence, but once again, they don't tell us much. They don't really tell us how to build intelligence from scratch. And this is the main reason why today we don't have AGI. We don't know how to replicate something that we don't know. It's a bit like magic for us. And we'll talk about this more later. But the truth is that we have managed to accomplish amazing feats in civilization because we understood the natural phenomenon and be able to replicate it. Like, for example, the fact that you can take amazing pictures with your phone, it's mostly due to the fact that we understood how the human eye works. So building an AI from something that we don't really know how it works, it's not really easy, right? It's like even the brain. We know a lot about the brain today, but still, we don't know how even simple cognitive processes like memory actually work. We know the brain, it's made of synapses. Each area of the brain does what, but it's a bit more like we know the hardware of the brain and not really the operative system. So there's still a lot to learn from neuroscience. So until we understand how the human brain really works with the help of other disciplines, it will be difficult to truly replicate intelligence in a machine. Even the word artificial, it's a bit tricky because initially artificial intelligence was born as a field to truly understand intelligence and replicate it. But today it's more about building something that you think it's intelligent and where you is who the customer. So all these companies that are trying to build these so-called intelligent systems actually their goal is not to replicate or understand intelligence, is to build something that you, the potential customer, think is intelligence. There's also a lot of misinformation out there. And one good example is the Sophia robot. So the Sophia robot is an amazing piece of robotic that can really replicate human facial expressions really nicely. But still, when you read up online or even watch those interviews, it feels like it's a human being. It's like an intelligent robot that can talk about anything and do pretty much anything, so much that even got a passport from the UAE, I think. But then the truth is that all these the interviews, like video interviews that you see, are pretty much staged. If you have the chance to really interact with this robot, is not as intelligent as it seems. So this is good and bad for us working in AI, because then when you have too much expectations from the general public, then you go through those so-called AI winters that we'll talk about in lecture 3. So the sad truth is that today, the way that AI understand language is not so much better than how a dog understands language, in the sense that, yes, ChatGPT and other large language model can produce a sentence much better than a dog and maybe even of most human beings. But in terms of understanding the meaning of those words, that's a far-fetched conjecture. And the reason is that we're mostly looking at syntactics, like as we'll see later in this lecture. A large language model is just something that is very good at predicting a sequence, predicting which word comes next, which sentence comes next, which paragraph comes next. And so is this how we produce a sentence? Not really. Think about translation. When you translate from a language to another, it's not like you do it in a sequence or word by word or letter by letter. You understand the meaning of a sentence, you encode the meaning, and then you decode it back into the target language that needs to be translated. So in reality, a lot of those so-called intelligent systems that we have out there today are truly just expert systems. They are very good at doing something, but they can't do much else. I'm talking about AI models like AlphaGo or even ChatGPT. ChatGPT is optimized for plausibility, for question answering, for as a dialogue system. It can't do much more than that. And that's exactly the problem with AI today. It's rather an emulation of intelligence rather than, sorry, a mimicking of intelligent behavior rather than trying to truly emulate intelligence. And you see this from the way many of these algorithms work. One prime example for this would be hallucination in large language models, but you can also see that in computer vision, like this example, this famous example here on the left of a very good computer vision system that can recognize people in images and videos, but for some reason, if you wear this colorful patch, the algorithm will not see you. So what does that tell you? The way this algorithm works is very different from the way the brain works. And these also bears questions of like, how much can I really trust these algorithm? And maybe clearer examples are in the case of adversarial attacks, where you just, if you know exactly how the algorithm works, you can just really change a few pixels in the image to really fool the algorithm into thinking that the image that initially it was correctly classified into something else that is completely wrong. So again, it's not just about the output, it's also how we get to that output. And that's why today many of us are working on so-called explainable AI. It's not just about having accuracy, but it's also about having explanations. So we can start with the limitations of AI to then move forward. And these are the four main limitations. So one is, as we mentioned, supervised, when you do supervised learning, or in general, when you do training of a model, like even a large language model or pre-trained language model, your model in the end is going to be as good as your data. So if your data is bad, and we'll talk about data in the last lecture, we'll talk about how data needs to be unbiased, comprehensive, and balanced. So if you have any of these problems, then your model, no matter how good it is in terms of the technicalities of the model, will not be good. It still have this dependency. It's not robust enough to go beyond the data. And this is also called the tank problem, because originally this was used in computer vision to distinguish, to find tanks in different images, and if the background was changing, then you would have you wouldn't recognize the same tank with different backgrounds. So again, we'll talk about this later when we talk about data, but having balanced and unbiased and comprehensive data is very important if you want to have a good model. Another big problem now that we have bigger and bigger models and deeper neural networks is that sometimes you have so many, like you have billions of parameters, and sometimes you just have to change a bit the configuration of the network, or stir the pile, and then suddenly the accuracy will improve and you don't even know why. So once again, this is more about interpretability than explainability. We'll talk more about this later, but having a model that is not just good in terms of accuracy, but also interpretable, it's very important, because then you don't just want to scramble the parameters and hope, cross your fingers and hope that things will improve. Another issue that is coming up with all these bigger and bigger models is that they are sometimes not reproducible. The core pillar of scientific research for the last 100 plus years has been that I come up with an idea, I implement it, I write a paper or a letter about it, and then anyone can replicate these results. But now with these huge models, it's very difficult. First, because you have a lot of parameters, and second, because it's really much dependent on the hardware. And so this has also become a big problem, especially in the scientific community. Sometimes it's very difficult to replicate a model into a different piece of hardware. But the most important issue, as I already mentioned, is the transparency. Many of these models, especially neural networks, are black box algorithms. They learn from the training data set, and then they work pretty well for classification, but we don't really know what's happening inside. Yes, we can look inside at the nodes and see how the weights of the nodes of the nodes change as I go through the training, but it's not like I can pinpoint a node and say, okay, this node is looking at this specific problem. It's just a distribution of weights, and unless you're working on explainable AI, these are very much black box algorithms, and you don't know how they come up with certain conclusions. So in the next few slides, I really want to talk about this. How does the neural network work? Again, I apologize to those of you who already know this, but it's just a 5 minutes crash course on how neural networks work. So I'm sure you've seen this image many times. These are the nodes that I was talking about earlier, and these are the edges that connects the nodes and of which I have to change the weights during training. So what happens in any of these nodes? The training, when I do training, I'm defining a threshold, and this threshold, as I do training, will move left and right in one dimension, so that later on, when I receive a new input, I can decide whether this node become active if the value that I receive as an input is higher than the threshold. So it's as simple as that. So in one dimension with just one input, this is not very powerful or intelligent. In this case, maybe I just want to build a heater that it will go on, or maybe an air conditioning system that it will activate only when there is a certain temperature. So this input here is the temperature. The things become interesting when I start adding more inputs. Let's say that I also want to add air pressure. Because I have two inputs, now I go from a one dimension to two dimension. And these are many of the examples that we saw yesterday. So here I still have this threshold that this time is in two dimensions. So it's a linear separator, as we've seen yesterday for naive Bayes and other algorithms. I add 3, and finally I'm in 3D. Each of these points, once again, is a point of 3 coordinates in the 3-dimensional vector space, but I'm still doing the same thing. Now my threshold is no longer a line, is a hyperplane, but it's doing exactly the same as before. It's cutting my space into 2 halves, one active, one inactive. So every time I get an input here, different numbers that represent humidity, temperature, and pressure, I can draw this data point in my 3D vector space. If it falls on this side of the hyperplane, the node will remain inactive. If it's on the other side, it will be active, so the information will be passed through the other set of nodes. So we're talking about multidimensional vector space because in reality, when we work with many documents or data points, we'll have more than 3. For us, mere humans, not so easy to reason in many dimensions, but you can think of this really as working in 3 dimensions. It's just that you have some additional dimensions that for a computer is not a problem to process. The very interesting stuff happens later when I start stacking more nodes. So I still have the same number of inputs, but this time I have 2 nodes. What does that mean? It means that I have 2 hyperplanes, and I can more specifically find those pockets of meaning in my perception space. So if the more nodes I add, the more hyperplanes I have, and then I can have a more fine-grained classification based on how my data is represented. So this should clarify what's happening inside the neural network, and also should also clarify why training is important, because if my training data is bad, all these hyperplane will be in wrong positions and nothing will work. And the next few slides, I also want to show you again the same, but from a different perspective. I'm sure when you were studying, if you ever tried to study neural network, you've seen a lot of these formulae. These are also matrices, same as we've seen before when we were talking about the vector space models and also the singular value decomposition. So why matrices? Actually, those matrices are just representing how those nodes are connected or disconnected. Here, for simplicity, I'm just using ones and zeros. So to represent which nodes is connecting to which other node, I can just have a matrix like this, right? This matrix is telling me which nodes are, which edges are active or inactive. So if let's take a very simple situation where there is a cook, maybe my flatmate that likes to cook these 3 types of food, how do I build a neural network to model his behavior? So if it's sunny, he cooks pizza, and if it's raining, he cooks burger. The first thing I have to do is to represent all these items, all this data that I'm going to work with as vectors. And this is actually an important step, because then when we use, for example, Word2Vec or any word embeddings, I'm given the word embeddings. But if I have to build them myself, then what do I do? In this case, if I have only 2 possibilities, sunny and rainy, I will have a 2-dimensional vector. 1, 0 is the sun, 0, 1 is the opposite, is the rain. If I have 3 foods, then I have a 3-dimensional vector, 1, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 1. So later on, I'm going to be working with these numbers once again, because the neural networks works with numbers. So I can later on, after all the calculations, reconnect these numbers to the actual objects. But here the key point is that for us, a pizza is so much more than 100. We have all our past experiences, the visuality of the pizza, the taste, the smell, how it feels to hold it in your hand, and so on. So a vector can represent, of course, the bigger the vector, the more granularity you have, but ultimately this is the biggest hurdle of AI today, is that these vectors are just there as a placeholder for some meaning that is not grounded anywhere. We'll talk about symbol grounding later. Now let's not get lost, and let's see how to build a neural network that does this. So in neural networks, I mean, if you want to just build a piece of code to do this, it's extremely simple. It's an if-then-else kind of situation, where if it's sunny, you cook pizza. If it's raining, you cook burger. But you build a neural network because then you can also be able to handle other different nuances. So for example, if I have an if-then-else piece of code in Python, for example, it can only manage those situations. But if I have some situation where maybe it's raining a bit, but it's sunny, then that's where neural networks are powerful, that they can handle all those situations in between, those kind of non-linearities that you can't do with other algorithms or just by writing code. But ultimately, what's going to happen inside is that I'm just going to do a multiplication of matrices. So if this is my neural network, which is this matrix that we've seen in the beginning, this one. Then I just multiply the neural network model for the sun vector 1, 0, and what I get is 1, 0, 0, which is pizza, and the opposite to get burger. So this is a very simple example. Of course, the neural networks is going to be much more complicated than this, but it is very important for 3 reasons. First of all, there is no real reasoning or understanding happening in there. It's just a mathematical model. And number 2, in order to start working on these real world items or words or whatever, we need to kind of translate those items to numbers, which is what we did here. And number 3, also what I said, the very first thing I said yesterday, that to do this, we are doing a kind of transposition from a real object to the numerical domain, do some calculations, obtain another number, and then go back to the original domain. So all the calculations are just numbers calculations, which is not what we do when we reason in our mind. Oh, I mean, that's debatable, but we always associate reasoning with true meaning and various experiences that we can have with those objects, even if it's like abstract concepts. But here I have no choice. I'm just going like we do in the Fourier transform. We go from a physical or real domain to the numerical domain, do some calculation, obtain another number, and then later on assign this number to the representative item, or in some cases the closest representative items if I have some no linearities there. Here in the next few slides, you see also how this can be represented using that graph that we had before. So this multiplication of matrices correspond to also using that graph, original graph that we were looking at before. And so again, this is something that is just modeling mathematically how we can handle those kind of if-then situations. So, are there any questions so far, or can I proceed? Do you want to take a break? The next few slides are going to be about deep learning. How did we go from neural networks to deep learning? So if you have a question about standard feed-forward neural networks, now it's your chance to ask. Okay, if no questions, we can continue. So this is another important concept. Maybe most of you are still young and just started hearing about neural networks when deep neural networks came about. But for those of us who are a bit older, like in my case, when I was studying, even during my undergrads, I was studying feed-forward neural networks. Then neural networks were kind of forgotten for decades. Why? Because there were other algorithms that were working better, and neural networks were just not very good at modeling some more complex problems. But now suddenly, with convolutional neural networks some 7 or 8 years ago, people became once again very excited about neural networks. So what's the big deal? What happened? Why now everybody is so excited again about neural networks? So this image summarizes what's happened, what's the difference. So last time when you are doing a classification a problem, like for example recognizing whether an image contains a car or not, what you had to do was some feature extraction or feature engineering, so that, for example, when you're doing the training, you have to say, okay, look for the wheels, the windshield, or any other important parts of the car to classify that image as a car. Now, the power of deep learning is that I don't need someone to do the feature extraction anymore. And in theory, that's good news, because then what was the problem with this? The problem was that you had to waste a lot of time, sometimes money, to ask someone to do the feature extraction for you. And also it could be biased because it depends on what different people think it's a good feature or not. In this case, with deep neural networks, it's a very bottom-up approach, learning from examples. So the more examples you provide, and the more the deep neural network, like a convolutional neural network originally, can do the feature extraction automatically. So this sounds great, but it's not like they always say in machine learning and AI, there is no free lunch. So this come at some costs. I can think right now of two major costs. Number one, I need so much more data than before. So before, even if I had maybe a few hundred pictures, I was fine with it, because then thanks to the feature extraction, I can easily cook up some machine learning algorithm that can be good enough to recognize cars in a picture. Now, since I don't have the feature extraction anymore, I need many more examples, because if I have too few examples, the thing won't work. I need a lot of example to understand what are the good features and the bad features. So this is one big limitation of using a deep neural network, is that you need so much more training data that you needed before. The second is that I no longer have control on which ones are the important features. So if you're doing some toy problem like this, who cares, right? You're just recognizing cars. But if you're doing something more important, like building a driverless car that has to recognize pedestrians, or some more fail-safe applications, or applications that involve ethics, then this is a big problem, the fact that you no longer have control on the feature extraction. And there are cases where this happened and it got a bad twist. One example was a AI company that was using an AI to shortlist candidates. And later on, only much later, they realized that the way the AI model was shortlisting candidates was it chose gender as an important feature to decide whether a CV was good or bad. But they didn't know, because it's a black box model, right? Unless you're using some special tools to increase the interpretability of the system, you will not know that the AI was actually biased towards gender. So gender is a feature that maybe if I had built the algorithm myself, I would have not put in as an important feature, obviously. And there are many other situations, like people that were more likely to be considered guilty just because they grew up in a certain neighborhood, and so on. There are many examples of these. We'll also talk about this later in lecture 3 when we'll talk about the AI winters. But in the next few slides, I will talk about exactly how we got from the standard feed-forward neural network that we just talked about to the deep neural networks and transformers. So if I'm not wrong, we are supposed to take a break now. Is that correct?
Yes, Eric. Yeah. We have a break now.
Okay.
Yeah.
So yeah, if there's no question, we can just take a break. And if you guys have, oh, Vivek has a question. Yes, please.
Eric, when you say feature extraction, do you mean vector representation of selected features? Is that the right idea?
Yeah, so again, feature extraction is a big word that can mean many things. There are feature extraction techniques, like for example the chi-square technique to decide, for example, which features are important. So if we're talking about documents, the chi-square will tell you whether a specific word is representative of specific probability density. But I'm talking about feature extraction more in general, like I said in this example, having someone that controls how the learning is happening and making sure that the way that we classify a car as a car is based on the parts of the car that are meaningful and not other meaningless parts like the background maybe in which the car is taken. So this relates back to the problem, the tank problem that we were talking about before. So yeah, I'm talking about feature extraction more in general rather than actual feature extraction and feature engineering algorithms.
Okay, thank you.
No problem. Any other question? Okay, if no questions, we can take a, how long? Half an hour break, right?
This half an hour break, Eric. Yeah.
Okay, so let's take a half an hour break and I'll see you later at, I don't know what the time will be in India, but it will be
11
2.
in India it will be 11:30. Yeah.
Okay, see you guys at 11:30.
Yeah. Yeah.
Everybody, please mark your attendance, which is shared in the chat box, please.